Greetings to every one of you. So in this video we are going to discuss another very important concept from data structures and algorithms, that is Floyd Warshall algorithm for finding all pair shortest path using dynamic programming. Let me explain what this dynamic programming is. Dynamic programming is a general algorithm design technique of solving problems defined by or formulated as recurrences with overlapping sub-instances. So any problem can be divided into the sub-problems, and the problems can be solved easily. So that is the concept. But again it is very much aligned with divide and conquer method, where we also do the same thing, but there is a difference. The difference is that in dynamic programming the sub instances will be done only once, but whereas in divide and conquer it will be done number of times. Okay, so that is the advantage of the dynamic programming over this divide and conquer. Now in order to solve this shortest path between all pairs of vertices, so consider this graph. It is a weighted directed graph, and if you consider 1 as the source vertex, and we can get 2, 3, 4 as the destinations. Similarly, if you consider 2 as the source, you will get 1, 3 and 4 as the destinations. Similarly, 3 as the source, we have 1, 2, 4 as the destination. Similarly, if you consider 4 as the source, you will have 1, 2, 3 as destinations. So actually the same kind of problem we have solved using Dijkstra's algorithm. It is a single source shortest path. But here the same algorithm maybe there is executed for all the 4 vertices, so that 4 times you have to execute the Dijkstra's algorithm. But whereas in dynamic programming we will do it once using the previous table values. We will incorporate those values, and we can get the next the table, and just we continue, and we will get the final result. So in order to solve this problem, first of all we have to convert the given graph into its equivalent adjacency matrix. So this is the graph is given here, and we are representing the graph in the form of a matrix, adjacency matrix. Consider this AD 0, the level 0. So see that since the graph does not have any self loop of any vertex, so make this diagonal value as 0. Okay, so 1 to 1, 2 to 2, 3 to 3 and 4 to 4 as 0, because there is no pointer from 1 to 1 or 2 to 2, 3 to 3 or 4 to 4. Make this value, diagonal value 0. Now get the values of other, the vertices from this graph. 1 to 2, it is 1 to 2, it is nothing but 3. If you don't have any direct connection, mark it as infinitive. So that is 1 to 3. We don't have direct connection from 1 to 3. It is a reverse arrow. The arrow is reversed. So we don't have any direct connection. So mark it as infinity. So there is similarly 1 to 4. That is 1 to 4. It is 8. So similarly 2 to 1, that is 9. Then 2 to 3, it is 2. 2 to 4, we don't have direct link. So that is infinity. So similarly 3 to 1, 3 to 1, it is 6. Similarly 3 to 2 we don't have direct connection, that is infinity. 3 to 4 it is 1. Similarly 4 to 1 it is 3. Then 4 to 2 infinitive. 4 to 2 we don't have direct link, so that is infinitive. So this is how we can represent the graph in the form of a matrix. So now from this matrix we have to proceed further, considering there is any vertex as the intermediate vertex. See, for example 1 to 2 we have a direct link. There may be a chance of getting a shortest path through another vertex, that is 3, or another vertex, that is 4. In between, that is 1 and 2. Similarly, for each pair we will have some other alternate path. So what actually we are going to do is we are considering each vertex as an intermediate or a pivot vertex in order to construct the other adjacency matrices. Okay. So in that way you are going to consider each vertex as a intermediate vertex, in which let us consider the vertex 1 as an intermediate vertex. Now we are going to construct the matrix, adjacency matrix, that is AD1. In order to construct this matrix, first thing you have to make the first row and first column. We are going to keep this value, that is vertex 1, as the intermediate vertex. So keep the first row as it is. Just to copy the value from the AD0. So it is 0, 3, infinity, 8. Similarly, the first column intact as it is. So make the diagonal values as 0, since the graph does not contain any self looping. Now you have to find out these values. Okay. So AD 0, this value is nothing but 1, 2, 3, 4, 1, 2, 3, 4. Okay. So find out this is the position. It is second row, third column. We have to include this vertex 1 as an intermediate vertex, so that we can write this AD0 2, 1 plus 1, 3. AD0 1, 3. So find out the value. This 2, 3 from here you have to get the value. 2, 3 it is nothing but 2. Okay. So AD is, that is 2, 1, it is 9, and 1, 3 it is nothing but infinity. So what happens, this 9 plus the infinity, so it is nothing but infinity. So infinity, the 2 is lesser than this value. So automatically we will consider that value as the resultant value. So 2, 3 it is nothing but 2. So similarly get the next value. It is 2, 4. AD 0 2, 4. This can be written as, that is AD 0 2, 1 plus AD 0, it is 1, 4. Okay. So get the values of this 2, 4, it is nothing but infinity. Then 2, 1 it is nothing but 9. Then 1, 4 it is 8. So it is nothing but 17. But 17 is lesser than infinity. So infinity is the existing value is greater than the calculated value. So automatically you perform the relaxation. This is what is called relaxation. So put this value there. So in 2, 4 it is 17. Okay. So similarly we can find out the remaining values. Okay, the table values. So 3, 2 it is 9, and similarly 3, 4 it is 1, and similarly 4, 2 it is 6, 4 comma 3 it is infinity, right? So what actually we got this adjacent matrix, that is 1. So from AD0 we got the value, that is AD1, keeping this vertex 1 as the intermediate, the pivot vertex. Okay, so now from this AD1 I am going to calculate this AD2, adjacent matrix, that is 2, I am going to calculate. Okay, so for that I need the value of this AD1, right? So the calculation, what you have to do, second row and second column must be, what's that, intact as it is in the AD1. You have to write the values. Okay, it is 9, 0, 2, 17. Second row, second column it is 3, 0, then 9, 6, and you know that the diagonal values are already 0 since the graph does not contain any self looping. Make this value 0. So remaining values we have to calculate. So like it is AD1, now AD1 of first row third column, here you have to, that is introduce the value of k is equal to 2. So that means you have to introduce the 2 as the intermediate vertex. So it is AD1 1 comma 2 plus AD1 it is 2 comma 3. So get the value, that is 1 comma 2. Write down the value from AD1. It is 1 comma 3, it is nothing but infinity. This is infinity. And write down the value, that is 1 comma 2, it is 3. Then 2 to 3, it is nothing but 2. So it is 5. So 5 is lesser than the infinity. The infinity is greater than, the existing value is greater than this 5. So now perform the relaxation, get the value, that is write the value, copy this value in the place of what's that infinity. So instead of infinity, now we got the value, that is 5. Okay, so similarly the next value is AD1, it is 1 comma 4. So it can be written as that is AD1 of 1 comma 2 plus AD1 of 2 comma 4. Get the value, just intermediate value, the 2 is what's that inserted in here. Okay, so now get the value, that is first row second column, it is 3, then second row fourth column, that is 17. Then what is the value of this 1 comma 4? 1 comma 4 is 8. So now the calculated value is greater than the existing value. So that being the case, no need to replace the value, just the same value is sustained there. The same value, you have to write it. So similarly, the other values for this AD2 are it is 6, 9, 0, then 1. Similarly, the fourth row, it is 3, 6, 8, 0. Okay, you can calculate the other values in the similar fashion. Okay, so now we got the AD2, matrix AD2, that is considering the second vertex as the intermediate vertex. Okay, so using this AD2, we have to calculate, that is AD3 matrix, that is AD3 we can calculate. So in which the same logic we have to use. Third row and third column, that is intact. Third row and third column, you write it as it is. So third column, it is 5, 2, 8. So the remaining thing like this diagonal values are that is 0. Okay, so now we have to calculate the remaining values. So remaining values you have to calculate. Okay, so here it is first row second column, that is AD3 of first row, second column. So now we have to introduce this third vertex inside. So this can be written as AD2 1 comma 3 plus AD2 that is it is 3 comma 2. So now get the values. So it is 1 comma 2. It is 1 comma 2 is it is 3 only. Now 1 3 is 5 plus then 3 2 it is 9. It is 14. But the value is the existing value, which is lesser than this. So what will happen, that value will be simply sustained. Same thing will be, that is retained there. Then similarly 1 to 4 AD3 of AD2 of 1 to 4 AD2 it is 1 2 3 plus AD2 it is 3 to 4. Get the value, that is 1 to 3 it is 5 plus 3 to 4 it is 1. So it is 6. This 1 to 4 is nothing but 8. So where 6 is lesser than this value, so now this 8 is replaced by 6. So similarly we can calculate other values. Okay, I will write down the values. It is AD3 for this is 8 0 2 and this is 3, and similarly for the last row it is 3, then this is 6 8 0. So similarly we can get the AD4, that is adjacent matrix 4, from this AD3 adjacent matrix, that is 3. So this can be written as the same logic we have to use. It is 0 3 5 6, similarly 6 0 2 3. This is 4 7 0 1, then 3 6 8 0. So that is the final matrix, so which will give you the final solution for this problem. Okay, so every time just we are performing this the operation, the relaxation, if the existing value is greater than the calculated value, then we have to replace. Okay, so here you can check the result. See, for example, if you want to check that is 2 to 4. So these are the rows and this column. For example, if you want to check what is the value of this 2 to 4, 2 to 4, it is 2 to 3 we have 2, and then 3 to 4, that is 1, we got 2 plus 1, that is 3. So similarly other thing like 1 to 3 for 1 to 3 there's 1 to 2 it is 3, and 2 to 3 that is 2, that is 5. You got the value. So similarly you can check the result with the graph. Okay, so this is the final result. So now how actually this can be done with the help of the programming. So what is the concept? So for just to consider k is equal to, that is 1 to n. Okay, so the next thing, that is for I is equal to 1 to n. Then the next loop in which for j is equal to, that is 1 to n. So inside which you are going to calculate the a of I comma j can be, that is equal to the minimum of, that is a of I comma j, comma, then a of I comma k plus a of k comma j. So take the minimum value of this, that is assigned as the a of I comma j. So we are using three different loops in order to solve the problem. So it is 1 to n, 1 to n, 1 to n. So just the order of the Floyd Warshall algorithm, it will be, that is the order of n cube. It's a time complexity. Okay. So since we have the for loops, I hope you understood the concept. I explained what is dynamic programming is and what is this all pair shortest path problem. Then how to solve this single shortest path using Dijkstra's algorithm, and how to, that is, derive this adjacency matrix from the the graph, and finally till get the solution. I hope you understood. Thank you.